let's see. Aryan, anything you needed to present today?
Yes, sir, I have a presentation.
Okay, why don't you start with that one then?
Okay, so it is about quantum chromodynamics. Hello everyone. My name is Aryan. I am 13 years old. I am living in Ludhiana for my education purpose, and I want to become an astronomer in future. So for today, our topic would be about quantum chromodynamics. So it is the theory describing the strong interactions between quarks and gluons. It is the fundamental aspect of the model of standard model of particle physics. It explains how protons, neutrons, and other hadrons are held together. Fundamental particles in QCD. So quarks are the building blocks of matter that carry a property called color charge. Gluons are the force carriers that mediate between the strong force between quarks. Both quarks and gluons are confined within hadrons and cannot be isolated. So, quarks are the force carriers of the strong nuclear force, and and they bind together the atoms. They bind together the protons, the neutrons. They carry a property called the color charge. So there are three fundamental colors in the color charge property: red, green, and blue. So they have anti counterparts to color charge and confinement. So it is analogous to electric charge but comes in three types: red, green, and blue. Confinement prevents quarks and gluons from existing outside hadrons. This confinement explains why we never observe quarks in experiments. So what? So if we try to pull, if we try to pull an uh, proton, what would happen? That the bonds in the gluon, the bonds which are holding the proton and the neutron together, are so strong. If we try to pull, they will pull harder, and if we apply enough force, they will just create counterparts. The QCD Lagrangian. So it describes the dynamics of quarks and gluons through Gauge theory based on the SU3 symmetry. It includes terms representing quark fields, gluons, and their interactions. The mathematical structure ensures local gauge invariance of the strong interaction. So gauge symmetry is, if we change the internal properties of a particle, what would happen? That nature would be forced to create an field, and that field would be called a gauge field. And the SU3 is the special unitary group of degrees. So it contains eight colors, and so it contains eight, and they are not nine because of the mathematics part. And with with eight colors of gluons, our universe is more stable, and that's why we have eight colors of gluons. Asymptotic freedom. So it means quarks interact weakly at high energies of short distances. This property was discovered in 1970 and earned the Nobel Prize in Physics. It explains why quarks behave almost as free particles inside high energy collisions. So what happens that if we try to pull an proton, what would happen that it will just create new counterparts. But if they're very tightly packed, the quarks can just move over each other, and it will create a superfluid has more which has less friction than any fluid on earth. QCDs at low energies. So the at low energies, the strong force becomes very strong, leading to confinement. non-perturbative methods are necessary to study QCD in its region. Phenomena like hydrogenization and formation of bound states occur at these scales. So non-perturbative means like very hard, the things that have very hard maths. And there is one more thing, that to solve these, we use lattice QCDs, which we'll discuss later in the presentation. So uh, at low energies, what happens that the a strong force becomes very strong, leading to confinement, which is observed in an hadron spore, quark gluon plasma. So it is a state of matter where quarks and gluons are deconfined. It is believed to have shortly after the Big Bang. Experiments like RHIC and the LHC aim to investigate and study UGP conditions. So, so it's a state where quarks and gluons are deconfined, which means that they can move freely. And there's one more question, that how are gluons present in the atom? So what is happening that that there's like a storm going inside the nucleus, which means like the quarks are orbiting the other quarks, and then the quark gluons are orbiting other gluons, and they're orbiting other gluons. So this is what is happening inside the hadron core. Lattice QCD so is some numerical approach to solving QCD equations by discretizing spacetime. It allows for non-perturbative calculations for hadron properties. So advances in computational power have significantly improved the precision of lattice results. Hadron structure. So the industrial structure of hadrons can be described by Pareto distribution functions. These functions give the probability of finding a quark or muon carrying a certain momentum. So deep inelastic scattering experiments have been crucial for probing hadron structure. Mesons and baryons. So these are particles made up of and one quark and anti-quark. Baryons consist of three quarks bound together by the strong nuclear force. Both types of hadrons are described within QCD with their spectra studied experimentally. QCD in collider physics. So it possesses dominant many it dominates many phenomena observed in high energy collisions. So jet formation is a key signature of quark and muon interaction. Precise QCD calculations are essential for identifying new physics signals. Spontaneous symmetry breaking. So chiral symmetry in QCD is spontaneously broken in the vacuum. This breaking generates mass for certain hadrons and affects pion properties. This phenomenon is crucial for understanding hadron and mass generation. So what is this symmetry? So quarks were originally meant to be traveling at the speed of light. But what happened that because of the vacuum of space time, there's one thing called the chiral condensate. So it is majorly present inside the nucleus, which is responsible for slowing down these quarks and other stuff. So what happens that due to E equals mc squared, it stores the extra energy as mass. So that is the mass uh, we see and observe. So anomalies in QCDs, quantum anomalies occur when classical symmetries are broken upon quantization. The axial anomaly has implications for mesons, masses, and decay processes. Anomalies help explain certain observed phenomena in particle physics. Topological aspects of QCDs. So it has rich topological structures such as instance influencing the vacuum. The, these structures may contribute to the mass of the N meson. Topology plays a role in understanding the non-perturbative vacuum properties. Experimental tests of QCD. Particle accelerators like the LHC and Tevatron test QCD predictions through collision data. So measurements of cross sections and jet properties verify the theory's accuracies. So can discrepancies can point to physics beyond the standard model. Challenges in QCDs, so non-perturbative effects, make calculations complex at low energies. Developing effective models is very hard, and there is an ongoing effort going on. So, chiral symmetry. So the particles spin in the same. So right-handed particles, the particles spin in the same direction as it moves. Left-handed, the particles spin in its opposite direction of its movement. So if quarks had zero mass, they would move at the speed of light. In this state, a left-handed quark would stay left-handed forever, and a right-handed quark would stay right-handed forever. The universe would treat these two teams as completely independent and equal. This perfect balance is what we call the chiral symmetry. So there are two teams, the right-handed team and the left-handed team. And if the quarks had zero mass, which we will discuss right now, they would have moved at the speed of light. And in this state, a left-handed quark would stay left-handed forever, and a right-handed quark would have stayed right-handed forever. And the universe would have treated these two teams as completely independent and equal. So this perfect balance is chiral symmetry. Breaking chiral symmetry, so it treats left and right handed quarks as independent weightless teams. In a cooling universe, the strong force made the vacuum thick with a soup of quark antiquark phase called condensate. This soup forces quarks to flip their handiness as they move, creating drag. This drag is the mass that builds protons, neutrons, and eventually. So there's one thing called the chiral condensate. So what happened after the Big Bang is that the strong nuclear force was too efficient for our universe. So it created a thick soup of quark and anti-quark pairs, which pop in and out of existence every time. And how does these things give quarks their mass? Is that whenever a quark is moving inside a hadron, what happens that there are in there are quarks anti-quark pairs moving. So it what it does is that it combines with an anti-quark, and then it reconstructs into a quark. And like there are only three quarks in an hadron. uh, like these are also called the valence quarks because the other ones just cancel each other out because of the quark anti-quark pairs. They pop in and out of existence. So what happens is that as this process happens, the quark should have moved at the speed of light, but it is not. So it means that it's it's getting slowed down, and it needs to store that energy somewhere, and that energy that we witness is called the mass of an quark. And and because of the chiral condensate, the universe exists as it is. We can touch anything, etc. So this is what gives quarks their masses. Metastable universe. So it is a cosmic state where a vacuum, the very fabric of space, is stable enough to last for billions of years, but it is not at its absolute possible energy level. As of 2026, current measurement from the Large Hadron Collider continues to suggest that we may live in a false vacuum. So we are going to the conclusion part of the presentation. So quantum chromodynamics is a fundamental complex part of modern physics. Ongoing research continues to deepen our understanding of this strong interaction, and it remains a vibrant field discovering new particle physics and cosmology. So, so that was the presentation. And ladies and gentlemen, do you have any questions? Hello.
Feel free to ask question. Anybody, please raise your hand. I don't see anybody raising hand yet.
Sir, someone has raised his hand. Rajni Jha. Hello, Rajni Jha. Hello.
Go ahead. Ask your question, please.
Hello.
Unmute yourself and ask question.
Sir, I am.
Hello.
What is your name? Just say first your name, because I know it is your mother's name showing here. What is your name? And then ask question what you have doubt.
Okay, sir. Okay. My name is Adarsh.
Okay.
Plan a nature walk with your teacher to a park or a nearby forest.
I don't understand your question. Is your question related to the presentation or something different? If it is not, if it is not related to presentation, then you should wait. When we will start general discussion, you can ask your doubt at that time. Right now, when somebody is presenting, then we only ask question on that presentation. So right now, we ask all of you, if you have any doubt about the presentation which Aryan just made, you should ask question about that presentation. Did you understand it? If you have any question about it, if you didn't understand, you have comment about it. You know, comment and questions are welcome. So please go ahead and keep that boundary in mind. Okay, who has question or doubt or comment? Well, if you guys don't say, then I'll give mic to Malik ji, and of course he will have several questions.
Good evening, sir.
Hello, good evening, everyone.
Good evening, sir.
So Aryan made a very good present introduction to quantum chromodynamics.
Yes,
How
sir.
did you learn, Aryan, all these things?
Sir, uh, sir, there are also always some books I read, and one time you also mentioned this quantum chromodynamics. So I got curious and searched about it.
Yeah, so even all aspects of quantum chromodynamics are still you know to be proved, but some are proved. So it's a very nice subject. So in
Yes.
future, people who want to take up something, quantum chromodynamics is one of the fields which you can take up. Well, thank you very much, Aryan. Very nice presentation.
Okay, sir.
Who else has questions today?
Sir, I had a question.
Oh my God, good. Okay,
So,
but are there some new people? I saw some new people there.
sir, I don't think so.
Yeah, they are all old people. We already have gone through introduction.
Acha, gone through all it. Rudra, I was saying, so is he new or is
Sir, I think so. Is he used to join.
okay? Yeah. So what is the question, Aryan?
So, sir, it's about the electroweak theory. So, what happens in that is that it picks up that when particles want to decay or do something, what they do is that they create or they manifestate the bosons, the P and the Z bosons. So when they do that, aren't they like? I think so. I think so. They are just breaking the laws of conservation of these things, because when that happens, we are taking that energy from the vacuum itself, because these pop in and out of existence, and if that happen if that's the case, that the energy is getting not, if the energy is not, the things are not conserved, So isn't that breaking some rules?
Yeah, I didn't know, but actually, I'm not very strong in this electroweak theory. I'm not very strong. I won't be able to answer this.
Okay.
The only thing that comes out in quantum chromodynamics is one of the few things. Whenever there is symmetry broken, by the way, you understand what is the weak theory? This weak force theory.
Yes, sir. Sir, the electroweak theory is the
No,
is the
not the electroweak. Okay, is the something which was integrated and became one. But by weak force, what do we mean by weak force? Weak
so sir.
force is a different kind of force
Yes.
compared to gravitational or the electric or the strong force. In the sense that uh, see, gravity is there. If the Earth is there, then the moon is there. So Earth attracts the moon by exchange of particles. It exerts and it exerts the movement. It causes movement to the moon. In the
Okay.
weak force is very interesting force. It doesn't cause movement. It just changes the state of that particle.
Sir, it causes movement.
Hello?
Yes, sir. Sir, I
So
was saying that it causes movement. It can cause movement.
that it exchanges particles,
Okay, sir.
W and G bosons.
Yes, sir.
And say one quark, which is say some things will become another kind of quark.
Yes, sir.
That is the cause, Madame Curie, when discovered radioactive decay, people did not know how to explain कि न्यूक्लियस में तो इलेक्ट्रॉन है ही नहीं, तो न्यूक्लियस से इलेक्ट्रॉन निकलता कैसे है? In radioactive decay, what happens? Alpha, beta, and gamma rays come. Beta ray is electron. Alpha. This is what we learned in school also. All of you might have learned.
Yes, sir. Beta decay.
Amarnath, you might also have learned radioactive decay.
Mhm. Half-life.
Alpha, beta, gamma rays come from the nucleus, but nucleus में तो इलेक्ट्रॉन ही नहीं है. इलेक्ट्रॉन आता कहाँ से है? They were
Hmm.
so puzzled about it.
So then, how did they? I think this is a good question to answer. Why don't you answer? What happened? How do you explain the radioactivity then?
Weak force, weak force gives a kind of exchange. Quarks they get nature change हो जाता है. Something up quark, down quark हो जाएगा, strange quark हो जाएगा, या charm quark, things like that, by exchange of particles. Exchange of particles is mostly W and G bosons.
Yes, sir.
So they just change. So weak force is very interesting in that sense. But later on, Abdul Salam came and he said that okay, weak force and electric force they are one. They are one and the same force. I still don't understand that.
What, sir?
Electro weak, electro weak, which you are saying, the electro weak, they got merged. Means they are similar kind of things. Similar
Sir.
in the sense that again there is the exchange of particles only in the electric as well as in the weak force. Generates the electric force, generates a field is generated. In the
Yes.
weak force there is exchange of particles. तो आपके बॉडी में भी जो पोटेशियम है, पोटेशियम जो है ना, आपको पता है माना जी, आपके बॉडी में जो पोटेशियम है ना K40, वो कैल्शियम में चेंज हो जाता है, it's getting because of the weak force.
Hmm.
आप जो केला वगैरह खाते हैं, केला has lot of potassium and it has got K40 also, बनाना. आपके बॉडी में जाकर के वो K40 कैल्शियम में चेंज हो जाता है. It's because of the weak force. There is a weak force acting in your body itself. Very interesting things. But आर्यन ने जो क्वेश्चन पूछा है उसका आंसर तो मेरे पास है ही नहीं.
Yes.
I will need to read and then answer your question.
Sir, uh, sir, I think, sir, I had a question for you.
Is it difficult or easy?
Sir, it's an opinion based. It's about your
Okay,
idea.
okay, yeah, sure, go ahead.
Sir, what do you think? Like, which equation is your favorite?
Which?
Equation is your favorite, or which caused the more, which is like more important in our universe?
I think the Schrodinger equation to me is the most difficult, least understood, most interesting equation that one meets in life.
Yes, sir. So, sir, is there any else any other equation?
और तो एक तो हो सकता है कि उसी के रिलेटिविटी का जो इक्वेशन है वो भी so that also of course E is equal to mc square is a very revolutionary equation.
Okay, sir. So, sir, uh, my
But
view,
yes, what is your favorite equation?
sir, I think so. The uncertainty principle. So I think so. It carries the back of all physics. So it is the reason that quarks have mass. It is the reason the forces, the weak nuclear force is there, uh, and there are way too many fields for this equation. So this explains a lot of things. The chiral condensate is based on it has a part of uncertainty and many other things. So I think so. It's pretty important. The uncertainty one.
Yeah, you see the uncertainty part is already embedded in Schrodinger equation actually.
Okay, sir.
Uh, because immediately it comes to a wave function, particles getting represented by a wave function itself, that itself is a statement of uncertainty principle.
Yes, sir. So
So Maliki, I have started doubting all the equations after coming to these meetings. You know how things you guys are explaining how physics is changing, how chemistry is changing, how everything is changing. We don't even know what we are, what are we made up of, right? All the traditional thinking we had about ourselves is now what you call out of window. So with that, there are so many unknown variables, which is the question to explain it correctly, which we don't know, or it is not possible with our limited sensual knowledge to have all those variables and their contribution to any equation. So I think we cannot correctly construct any real equation which can explain these new things. And especially when it comes to astrophysics, I doubt any of those equations are 100% correct. They are partially correct, but not 100%.
yes, sir. So sir, there's an effort going on right now. It's the planned unification of all the forces for the theory of everything. So right now we have only done three, but we are trying to do the fourth one, which is gravity. And we have tried the bag of tricks that Feynman gave us. So we did that, and we solved for the three. But right now, the normalization trick that Feynman gave us did not work for gravity. So we are trying new bags of tricks by other physicists, but it's still a long way.
I also want to hear from the other guys. There are a
Amarnath
lot of,
ji,
yeah,
I'll make a comment on what you said because young kids are there. So actually, what is happening that let us say in 15th century, people came to the conclusion कि जितना भी जानना था हम लोग सब जान गए, अब कुछ जानने का जरूरत नहीं. And you see, then Copernicus comes
right.
And he says that you see, it's not the sun going round the earth, it's the earth going round the sun. And
Yeah.
you'll be surprised, Copernicus लोग उसके दिमाग में जब ये आइडिया आया तो वो डर गया एक्चुअली कि हम लोगों को कहेंगे तो लोग हमको मारेंगे.
Mm.
So he expressed it, you know.
Yep.
But वो जो calculation what he was doing, it was showing that it is not the earth which is sun which is going around the earth, but it is the earth going around the sun. So he was very much afraid, and then he started searching old books, 1,000-year old books कि कहीं पहले जो बड़े बड़े आदमी एरिस्टोटल सोक्रेटिस उन्होंने कुछ कहा है कि नहीं. Then I can
Mm.
take their name and then promote my tell my
Idea.
thing to others. Yeah,
Yeah.
tell my idea. Then I will
Yeah.
get less beating, you know.
Yeah.
But
Yeah.
वो
Smart way.
बेचारे कौन
Yeah.
ये कॉपरनिकस
Absolutely.
नाम खिंचा कर.
Ah.
So he kept on thinking about it, and he did. Finally, he wrote the book, and that book was even वो नहीं होता है कि dedicated to a bishop.
Yes, I think so it was
Because he
something about
thought
witches.
if I give to bishop, there will be less criticism from the church. करके छोड़ दिया, वो भी भूल गए, सब भूल गए. उसके मरने के बाद जो है ना, वो that book was read by people, by the Christian people, and they said, अरे what he has written is against Christianity. And तब चालू हुआ उसके बाद जो है ना, but people started supporting because by the time Galileo भी आ गए और ये सब आ गए, Newton आ गए, and they started saying. So that's how his thing got to. Same situation arose in the 19th century also.
Mm.
कि जब रेडियो एक्टिव डीके ये सब मिल गया, क्वांटम मैकेनिक्स का जन्म नहीं हुआ था, लोगों ने कहा कि अब तो हम लोग जान गए एटम क्या होता है, सब कुछ जान गए, अब कुछ जानने का जरूरत नहीं. तब क्वांटम मैकेनिक्स आया एंड क्रिएटेड होल रेवोल्यूशन.
Mm.
सो हम लोग जो फील करते हैं ना, एक्चुअली बेसिकली वी आर गोइंग डीपर एंड डीपर इनटू द थिंग्स. सो मेनी थिंग्स आर गेटिंग एक्सप्लेन्ड, मेनी थिंग्स, नया नया चीज आ रहा है, वो चलता ही रहेगा. We don't know how long it will be going on. But we are
Yeah.
certainly much better off than before because we
Yeah.
understand and we are applying it. Now you see the quantum mechanics ka application in quantum computing. It seems artificial intelligence का maximum use तब होगा जब quantum computing will become very popular. It's going to change the whole society in a very different way.
Yes, sir.
We are certainly not prepared for it. हम लोग तो prepared हैं ही नहीं, और younger generation also will face it.
Sir,
Yes.
sir, there are few questions by two people, Saksham and Earth Raj.
Yes, Saksham, please go ahead. Earth is also there. I can see that. Yeah, both of you. Who wants to raise the first question?
Sir, can I?
Hello? Yes, go ahead. Earth is asking the question.
Yes, sir. Sir, my question is that why can we see lightning before we hear the thunder?
Why we can't? Why we can see lightning before thunder?
Yes, sir.
May I answer, sir?
Yeah.
This is
I think
yes,
this
please.
student should answer it. Yes.
Yes,
See,
yes, very good. Please answer.
yeah.
Lightning and thunder occurs at the same place, but we see it differently because the speed of light is more than the speed of thunder.
Speed
What
of
is
Hence,
sound.
thunder?
yes,
Speed
sir,
of
Speed of
speed
sound.
of
sound.
sound.
Yes.
The speed of light is 3 lakh kilometer per second, and the speed of sound is 322 meter per second.
So are you satisfied, Earth?
Yes, sir.
So it is like, imagine if there is a race going on, somebody is in the car and he is racing with a person who is just on foot. Who is going to reach on the destination first? Arthraj?
Uh,
Yes, sir.
Arthraj. Who is
Yes,
going
sir.
to reach first? person who is in the car or person who is running on foot?
Sir, that depends on the speed of car and the speed of the person.
Let's say that both are running at very high speed. Maximum speed they can walk, they can run. The car is running also at the maximum speed possible in that area, allowed in that area, and the person is walking also with the maximum speed. So who is going to reach the destination first?
Sir, car, the person who is sitting in the car.
Okay. So car is, what you are saying is that car is going to reach first because the car has a higher speed than the person, right? Is that what you are saying?
Yes, sir.
Okay. So that's exactly what is happening in the case of lightning. It has two components. It has sound component and it has light component. So light travels many times. We have discussed here much more faster. And what is Astha? Who is Astha Ankor? Yeah, he explained to you that that is faster, many times faster than the sound. So that's why you see lightning first. Okay, who is next?
Saksham.
Saksham, please go ahead.
Hello,
Sir,
Saksham.
my question is how does a quasar tsunami occur?
What?
Sir, my question is how does a quasar tsunami occur?
How does
I think
Quasar?
Aryan can answer this question, right? Aryan, can you please?
Sir, I didn't get the question. What he said.
Sir, my question is how does a quasar tsunami occur?
How does it?
Quasar tsunami. Is that right?
Well,
Yes, sir.
So you have to understand first tsunami. Everybody, do you know what is tsunami?
Yes, sir.
Yeah, let Saksham only answer what is tsunami.
He asked the question and now we got the question. So what
Yeah,
is tsunami?
these are
Give
very
us with example, what is tsunami first? Because not everybody knows.
Sir, tsunami is a gigantic wave which occurs either in the sea or in the extremely large lake like Aral Sea or Caspian Sea. Tsunami occurs due to four ways, either by earthquake or by landslide or by underwater volcanic eruption, or you can say the asteroid impacts.
So you see,
It,
he had answered it also. So you have answered. How does tsunami occur?
yes, sir.
Thank
But
you
now
very
he is
much.
relating to
no, sir. He
quarks,
is
right?
asking.
Yeah.
He's asking,
What is
how does a tsunami? How does a quark tsunami occur?
No, my question is how does a quasar tsunami occur?
Yes, quasar tsunami.
Oh, I don't know what is a quasar tsunami. I haven't. Does
Sir, I have
anyone know?
heard, as far as I heard, I only knew that it is one of the most energetic events occurring in the universe. So I wanted to know how does it occur.
So I think so. As the name suggests, it involves a quasar eating a lot of stuff, and it's radiating. Maybe it's radiating high amounts of energy that repels outwards. So that can be a tsunami, quasar tsunami. Maybe that's the case.
Quasar is normally radiating extremely high radiation, but in quasar tsunami, it radiates the radiation not much higher than it normally it. How does it happen?
Okay, how does that happen? So around the accretion disk, what happens that the material, the gas and the materials get accelerated to near light speed. They get near light speed acceleration. So that might be one of the reason why it's so high. The energy is so high.
Yes, if yes, I think yes, we know that the gases near a quasar can reach the speed 90% the speed of light. But the quasar tsunamis occur sometimes when the black hole is emitting too much radiation. How does it happen?
Emitting too much radiation. Okay.
Yes, it has been observed that black hole when quasar is emitting too much radiation, quasar tsunamis are seen. So why did it happen?
Okay. So I think so. There's one concept I forgot its name. When a black hole emits way too many charge, and if we try to what you call put in another mass with that same charge, it will repel. It will repel it to maintain the universal laws. So and if the gas tries to fall it will just repel it.
There
That's
is
sir.
okay.
What do
There
you
is
think?
a question from Archana. Are you satisfied? There is a,
No, sir,
I
I
can
was
see.
not satisfied with audience.
Yeah, Aryan is he is not satisfied.
I guess we need more research. So why don't you guys kind of start thinking about it and maybe come back? Let's say what Aryan has thought on it and what uh, Saksham has. So maybe we should continue this discussion next week and following week also.
Yes,
Good
sir.
topic. Yeah,
And there is one raised hand, Archana.
Yes, sir. He forgot
that
to.
is Saksham.
Yes, sir.
That is
Saksham, yeah.
Saksham.
Hello, Saksham.
What
Yes,
else?
sir.
So,
Sir,
what is
I
the
had
question?
one more question
Sir,
that
he
suppose
already
if
asked that one.
sir, I had one more question that suppose there is an asteroid 100 meters wide and it is going to impact the Earth. So how does scientists know what will be the size of the impact crater?
Okay, I think so. Uh,
That's that should
I
be much simpler. I think Aryan, you should be able to answer this question, right?
yes, go ahead, Aryan. You want
sir, I think so.
So
We,
he's giving you the dimension of the asteroid, and he's
okay,
saying that how big it will create crater on the Earth. Suppose if
My
uh,
question is suppose there is an asteroid 100 meters wide and if it hits Earth then how will we know that what will be the size of crater?
okay. So we can, if the height is given, I think so. Uh, we'll estimate its mass and we'll find out the energy the energy before hitting the ground, and if we calculate where the uh, uh, asteroid will hit, we can calculate by the density and the other things. And when it when it impacts Earth, we can that way know how big the crater would be.
yeah, I will tell you something in physics. You know, जो meteorite का जो है ना 100 meters का है. So what happens is that what one needs to know what is the mass of it and what is the velocity. So once you know the mass and velocity, the impact which it makes, it is a problem in pressure physics. You have heard of so many physics. There is also one pressure physics, high
Okay, sir.
pressure physics, they call it high pressure physics. So they study these phenomena that if there is a huge, it is a kind of huge pressure being created by the impact. So how a particular material, like say the Earth's surface, or if it falls on a in the sea, what will happen? They all do these kind of calculations. Or when an atom bomb explodes, so that is also a high pressure phenomenon. So they calculate all these things. It can be calculated roughly, not exactly, but roughly. Yes. Amarnath ji is presenting some pictures of the craters created by the meteorite. You see,
See the this one is Arizona crater. I think Malik ji has gone there. I have also gone there. We have seen this crater. So basically, there was a asteroid which attacked planet Earth, and then it created this depression or hole. And uh, so you see that interesting part is that pretty much it looks circular.
Yes.
Sir, I had one more question.
What is that?
Sir, my question was, does life near a black hole or a quasar is possible?
What is that he's saying?
Is life near quasars and black holes possible?
Or this one you want to answer, Aryan?
So I don't think so that life could exist near a quasar or black holes, because if it releases a burst of gamma radiations, it will kill the living organisms on it. And even if there are planets with good atmospheres, I don't think so it would uh, be able to withstand these circumstances. The chances are the chances are pretty low, but I don't think so that we can discover any.
But what will happen if the life is several kilometers beneath the surface of the planet, like in the Haitian world?
Okay, so uh, deep back, deep ice bacterial cells may survive. So, so I don't. So I think so. They can survive if they are underground and the planet has a good atmosphere and these things.
There is another question coming. Where that is, sorry, Archana.
So Rajni, it's Adarsh. Rajni, tha.
Others, hello, please, others. Yes, go ahead with the question. Hello, others. Hello, others.
Yes, sir.
Yeah, what is it that you want to say?
Sir, I
Amarnath ji.
have a question.
Yeah, what is that?
Write about a similar problem that you tried to solve.
Sorry, can you repeat the question once again? Is it a problem I
Okay,
am
sir.
having with my mobile or Pankaj ji, or is it universal problem?
Write
Sound
about
right.
Be close to mic. Your microphone or phone, whatever you are using, please talk being close to mic. That will reduce the distortion of sound. We're not able to hear you very well.
Sir, I understood his question. So he was
Okay.
saying that what is the one problem that you have tried solving? I think so. That's the question.
Oh, so whom are you asking this question?
So it was asked by Adarsh. I don't know who he was asking.
Hello, others. Whom are you asking this question? Hello, others.
yes, sir.
Yeah, this question you have asked to whom?
Sir, this
Hello.
question is repeated.
Uh, whom did you ask this question?
Sir, this is repeat.
This is a repeat. No, sorry, I'm not getting. अच्छा अमरनाथ जी is presenting something. अमरनाथ जी आप बताइए
Okay, so this is another crater picture I'm sharing. This is from Oregon. It is such it is such a big crater that there are several towns around this lake. Now this is called Crater Lake. So this was also one time hit by meteoroid. I mean, there is a history there. You guys can on the internet you can find out about it, but I don't remember it. All I know is that I stayed on one of the motel or hotel on one of the bank of this lake. Okay, it is a tourist spot. A lot of people come and do like boat ride and all those kind of things. There are medium size ship which you can go on cruise and all that kind of stuff. So all over the world, there are several examples of craters which was hit by meteoroid. And in fact, it is very simple experiment. You all can repeat yourself. Let's say, for example, you take a small pebble, a dhela, to take a dhela or a pebble and and drop it in the water pond. Okay, take a little bigger size, like two, three different size of dhela. You will see, or pebble or rock. You will see that they create a different size of what you call bulbula in the water, and you can easily see that crater it creates, small and large and medium. So that is exactly the same principle works when asteroid hit the planet Earth. Of course, the medium is different. It's coming in the air and hitting the ground, not on the water. But you can calculate the incoming forces. You can calculate the resisting forces, and then, like Maliki said, there is a greater science. You can um, easily compute how much is the force and what kind of depression it is going to create. This is actually now a old science. This is not anymore new science. Okay. So what is time now?
okay we have 5 minutes time. So I want that you all should learn about something. Have you heard of cosmic microwave background?
Yes, sir.
किसी ने किसी ने सुना है आर्यन
Yes, sir.
क्या पता है आपको
Yes, sir. So, it's
डीप में
an
बताते हैं. I want you to learn these things, and we all should learn. I mean, this is for a common interest. This is one of the proof why people are still clinging to Big Bang theory. And this background, this microwave radiation which we observe, was created after the Big Bang.
sir.
So,
It, sir.
so
One. Uh,
yeah, you want to say something?
yes, sir. The thing you mentioned about the Big Bang. So, in Newton's time, there was someone had raised a question, and it was like, why is this night sky dark? So, someone asked a question, and Newton tried to answer this, but he failed. And there was some another person. He told that light would have taken, uh, if the universe was infinite. The light, like if it had an infinite past, light would have already reached us. It means, so with this small statement, he just proved that the universe had a finite past. So I think so. it was in the book that I was reading, The God Equation by Michio Kaku. So the lines you just said, it made me remember them.
अच्छा, तो आपको हम बताते हैं कि कॉस्मिक माइक्रो बैकग्राउंड क्या चीज है. You see, some time back now, I don't remember the year because they were given Nobel Prize for this. See, there was a gentleman, he was trying to look into there are, X-ray telescopes, there are gamma ray telescopes, there are light telescopes. So there was a gentleman, he was the microwave side में कितना आता है यूनिवर्स से कितना आता है. So what he found is that his instrument was catching up all the microwave from wherever, which direction he points. He found that there is some microwave coming. So he was very much surprised कि ऐसा कैसे हो सकता है कि माइक्रोवेव किसी स्टार से आएगा तो एक डायरेक्शन में आएगा ना. सारा जिस तरफ ही वो एंटेना को घुमाता था वो सभी डायरेक्शन से माइक्रोवेव आता था.
Mallik
So
ji,
yes,
I just want to add that this experiment happened here in Edison, in Thomas Edison's lab in 60s. So this is well, you
yes,
have come to Edison. So yeah,
somewhere there. But
yeah.
see, they were very much surprised. They were basically electronics people, basically. Electronics having interest in physics. So वो जिधर भी टेलीस्कोप को घुमाते थे उधर से माइक्रोवेव आ रहा है. तो वो लोग सब कंफ्यूज हो गए कि ये जरूर इंस्ट्रूमेंट में गड़बड़ी है. सो दे स्टार्टेड लुकिंग इनटू इट. इंस्ट्रूमेंट में कुछ गड़बड़ी है या दिखा रहा है ये. तो कितना भी खोजे नहीं मिला. Finally they started searching in many ways. जो उस समय सैटेलाइट भी जो ऊपर गया वो भी रिकॉर्ड किया. And many other people recorded. It was put in the news journal and people recorded everywhere. Then they started thinking that what is this. Then they came to a conclusion. The explanation which was given is very very interesting. शुरू में जब बिग बैंग हुआ तो क्या हुआ. What happened is that there was no atom तो था नहीं तो लाइट कहाँ से आया. It was just after few microseconds. It was all quark and gluons and all that. तो जब एटम जब बना धीरे धीरे, when the universe started cooling, इतना टेम्परेचर था कि एटम बनना मुश्किल था. तो जब कूलिंग जब चालू हुआ तो एटम बनना चालू हुआ. जब एटम हुआ तो लाइट हुआ. That light is still traveling in the universe. वो जो बिग बैंग का था, but that was, let us say, the higher frequency, but lower frequency कैसे हो गया. Because the earth is expanding, तो वेव जो है ना वो वेवलेंथ बड़ा हो जाएगा ना. Are you able to figure it out? See, suppose the atom emits a wave in, let us say, light frequency. But if
Yes,
the space is expanding, that wave will become bigger and frequency will become less. Microwave.
yes, sir.
वो माइक्रोवेव जो है, so उस समय जो फॉर्म हुआ लाइट जो फॉर्म हुआ वो अभी तक दुनिया में यूनिवर्स में घूम रहा है. And that is the microwave coming from all the sides, everywhere.
Yes, sir.
And he was given a Nobel Prize. In fact, the some people who understand what is a black body radiation, it corresponds to about 3 degree Kelvin.
Yes, sir.
Like the sun has got a temporary light emission corresponding to 6,000 degree Kelvin. The microwave radiation which we observe is corresponding to 3 degree Kelvin. Which Earth, क्योंकि universe is expanding, is one of the proof why why people say that the universe is expanding.
Yes, sir. Hello, sir.
So there are two proofs, that the universe expanding. You also know, एक तो हुआ cosmic background radiation, and the
Yes,
other one is that the red shift जो होता है. So these two are the proofs. But who knows? Who knows in future? Suppose something new theory comes which explains this. We'll have some other theory, but there is something very some proofs are there that the universe is expanding. There is a proof existing. and for the Big Bang also. मैंने हवा में बातचीत नहीं हो रहा है, मैंने there is some proof existing.
So, sir, isn't this
अभी हम एक जगह गए थे अमरनाथ जी, वो लोग बोले आप कैसे जानते हैं कि अब बिग बैंग हुआ था? ये सब मन गढ़ंत कहानी है। उन्होंने क्या बताया हमको कि असल में क्या है कि असल में वेद में लिखा हुआ है कि ब्रह्मांड माने ब्रह्मा और अंडा, उस अंडा से ये हुआ है। दैट इज मोर करेक्ट कंपेयर टू बिग बैंग। So it was a very interesting discussion about Ved and Big Bang theory.
वो तो
sir?
होता ही है ना। Yeah. Basically, when you challenge as a scientist to the religious belief, they are coming from belief system. We are arguing based on the scientific facts, so they will collide, and then of course there will be disagreement. Yes, Aryan, you have a follow up question.
So, sir, isn't this a direct proof that energy conservation is not uh, applicable on a global scale? Like the visible photons that the atoms released way back was stretched, so it meant that it made the longer wavelength. So where did that extra energy go?
No, sorry, atom was not stressed.
No, sir, the wavelength.
Atom, see, for light to generate, you need to have an atom actually.
Yes, sir.
Because unless the atom is not there, because earlier there was no, there was a 200 million years, and then more than that, the universe was completely dark. There was nothing, no light at all, absolutely.
Oh,
जब एटम जब फॉर्म हुआ उसके बाद लाइट जनरेट हुआ, वो लाइट है ये. इट इज नॉट दी, आई डिडंट गेट योर क्वेश्चन. इट्स नॉट द एटम. तो अब वो जो फ्रीक्वेंसी जो एमिट कर रहा है ना, बिकॉज द स्पेस इज एक्सपैंडिंग, यू नो, सो दैट वेवलेंथ, शॉर्ट वेवलेंथ जो होता है ना, वो लॉन्ग वेवलेंथ में हो जाता है.
so
जस्ट
sir,
लाइक डॉपलर शिफ्ट, just like similar to the Doppler shift. So
so,
you
sir,
all, when you grow big, you must learn. You should try to learn more about the Doppler shift and all these things. They are very interesting things.
so sir,
Yeah,
the
what is it that you are saying? Yes,
so sir, the short wavelength gets big. So it means
because of
that,
the space is expanding. Yeah,
so sir, where does that extra energy go?
it doesn't go. It is moving in the universe.
So no, sir, where does that extra energy go? We know that short wavelengths correspond to high energies and longer to lower. So isn't this a direct uh, violation of the fundamental laws that energy must be conserved because it just disappeared out of nowhere?
Let me just think about it. What you are, so if I can phrase your question is that earlier, let us say the energy of the photon was h into nu, h into frequency. Now that frequency has changed. Is that what you are saying? Because the wavelength has increased,
Yes, sir.
so frequency has decreased. So h nu is less.
Yes,
Let
sir.
me just think about it. Maybe I can answer it next time. Let me just think about it.
Sir,
Good
uh,
question. Good question.
so sir, like, what do you think about that? Is the conservation laws applicable on global scales?
No, you see, all the conservation, earlier there was a conservation of mass,
Yes,
conservation of energy. Finally, we found that neither the conservation of mass holds nor the conservation of energy holds. So
yes,
they keep on changing. So once we get new things, we detect, we have to know whether it conserves or not. It
so
can
sir.
happen. Not that there is nobody to stop to say that there in future we might observe an event. अभी तो साइंस इज सो यंग,
Yes,
200-300 वर्ष पुराना है.
oh, yes, sir.
The earth is 4.5 billion years वो अभी टाइम हो गया है, तो नेक्स्ट टाइम आई विल टेल यू अबाउट द हाउ द एज ऑफ द अर्थ वाज मेजर्ड. आप लोग भी पढ़ के आ जाइए, बहुत इंटरेस्टिंग
Sir, we
किस्सा
have
है.
already answered that.
Yeah, I'll tell you the story about it. A gentleman called Claire Patterson.
Yes, sir, I heard that. I have heard about the
It's a very
stories.
interesting story. I'll tell you next time
He
with
also
some.
led. He also
Yeah,
led
please,
the planning of
please,
lead.
please, please read it. See, he was a gentleman who should have been given a Nobel Prize, but
Yes.
nobody knew about him. But he was the one who found out ways to find out. But more than that, he discovered. अमरनाथ जी, आपको पता है ना कि पहले जब हम लोग स्कूटर चलाते थे तो आता था ना कि पेट्रोल, लेड वाला पेट्रोल और बिना लेड वाला पेट्रोल.
Yes.
Hmm.
सारा जिंदगी जो है ना वो इसके लिए लड़ता रहा कि लेड को जो है सो यूज नहीं करना चाहिए, बिकॉज लेड इज न्यूरोटॉक्सिन, यू नो. It
Yes.
decreases the IQ of children. It can create lots of brain damage. But he was the one who found out the age of the universe. And very interesting तरीके से find. I'll tell you next time.
Yes.
अभी तो 9 बस 9:30 9:15 बज गए.
Yes. The session
Yeah,
is
I
over.
think we can conclude. So, kids, you guys can drop off now. I want to ask Malik ji some question about the politics of West Bengal election. What's going on there? So,
The session is a question.
all
Sir, I
right.
had one.
Yes, go ahead with the question quickly.
Sir, my question was, what is iron 56?
You mean
What is, what is iron 56?
Yes, sir.
Yeah, you see, every element, you know, has a mass number. By mass number, it means how many protons and neutrons it has. So number and every element has got so many isotopes. Like say for example, मान लीजिए लेड को ही ले रहे थे, बात कर रहे थे. There are 40 isotopes are there. हाइड्रोजन का देखिए, हाइड्रोजन, ड्यूटेरियम, ट्रिशियम, so many isotopes are there because the number of neutrons are different, so different isotopes are formed. So iron 56 means there are 56 number of hadrons, protons and neutrons.
And sir, I had one question that in the does the formation of the hypernova is similar to supernova?
what?
Hello.
Sir, I have one question that the formation of hypernova is similar to supernova.
I don't know the answer to the question. Such I don't know the answer to this. This is too
I did
big
not
a question for me.
I did not get his question.
They asking hypernova and supernova are the same thing or not?
Okay.
No, sir, my question was, does the formation of both hypernova and supernova are same?
I don't know. I don't know. Can someone say?
So I think so. They might be same because if the right now the universe does not allow for a lot of mass to gather in one place so that the core becomes a black hole. So I think so it happens because it ran out of the fuel. Get me?
Okay, now it's time to wrap up. Time you should come up with questions which are around you, in your house, in your school, on the road.
Okay, sir.
I have one question for you all, for Saksham. Why is the rainy clock?
Sir,
Are
what is the
clouds
question?
My question is, why are the rainy clouds, they look black?
Sir, I think rainy clouds are black because they carry lots of water in it.
Well, this is not the answer, but you must give us the answer next time. क्योंकि बहुत वाटर होने से थोड़ी कोई ब्लैक हो जाता है.
Yes, sir.
So we are rounding up. Next time again we meet on Saturday.
Okay, sir. Bye, sir.
Bye. Best of luck to